Hello everyone. Let us today understand few basic facts regarding crystalline structures. Now, in the very beginning, I'd like to tell you what is crystalline structure. Now, you know that solids are broadly are of two types. The number one, amorphous solids, and number two, crystalline solids. Amorphous solids are those which are found mostly in some powdery form, or some it is not found in powdery form, but still their internal structure is very irregular. And if you look at the internal structure of amorphous solid, you will find that the atoms or molecules are not arranged in regular pattern. So arbitrarily the atoms or molecules will be placed. So this is the structure of amorphous solids. Now come to crystalline solid. Crystalline solids have a structure, internal structure, which is very organized, or you can say that it follows one definite geometrical pattern. For example, this one. The atoms or molecules are arranged in some array, and if you take any smallest unit of such arrangement, and if you extend this arrangement or that unit in all directions, then you will be obtaining the whole crystalline structure. So that is the very basic property of crystalline solids. So some amorphous solids are in powdery form, some are not in powdery form, but even then, even if it is it looks like a crystalline solid. For example, glass is amorphous, and if you look at the internal structure, then you will see that it is of this form. So this characterizes the amorphous solids. But if you take the example of crystalline solids, always it will be following a regular geometrical pattern. For example, sodium chloride. Then other examples of crystalline solid, you can take diamond, etc., etc. Right? So this is a very basic difference between amorphous and crystalline solids. So next, let us come to the idea of unit cell. So this is actually one crystalline structure in 2 dimensions. If you consider in 3 dimensions, then it will be something like this, right? The smallest unit which you get in 2-dimensional case is rectangular, or maybe square sometimes. So now let us come to the properties of crystalline structure. So as now we have learned that crystalline structure has a regular geometrical pattern, and along one particular direction the properties are same, because if you consider the interatomic spacing or intermolecular spacing, it will be seen that in case of crystalline structure, this distance is equal to this, is equal to this. Similarly, this distance will be equal to this and this, right? And similarly, along this direction, the distance between these 2 atoms is same as this between these 2 atoms, and so on, right? So that is why since along a particular direction the distances between atoms or molecules are same or similar, so crystalline solids are highly anisotropic. Anisotropic means that the properties are same in one particular direction, and it will be different along another particular direction. That is, it is not uniform in all directions. It is not isotropic, that means. But on the other hand, amorphous structures are isotropic, highly isotropic in nature because of its irregularity in the internal structure, right? So after that, let us move to the idea of unit cell. So what is unit cell? It is the smallest unit in crystalline structure from which if you extend the same pattern in all directions, you should get the whole crystalline structure. Okay, so that kind of smallest unit will be called unit cell, right? And so therefore, if you take the example of two-dimensional case, so your unit cell will be in two-dimensional case this one. This will be your unit cell in two-dimensional case, because if you repeat this unit in all directions, you will be getting the whole structure, right? So that is unit cell in two-dimensional case, right? And in three-dimensional case, it will be something like this. So this is one unit cell in three-dimensional crystalline structure. This is a real crystalline unit cell. Okay, and unit cells, if you know what is the nature of unit cell, what are the lengths of the sides of the unit cells, and if you know what are the angles made by the different bound surfaces of the unit cell with each other, then of course you know the whole crystalline structure, because repeating that unit cell you get the whole crystalline structure, and therefore you can also determine their properties and all. So after learning what is unit cell, now let us know what are the types of unit cell. There are two basic types of unit cell, primitive and non-primitive, right? Primitive means if you have the atoms or molecules only at the corners, then that is called primitive unit cell. And if you don't have atoms only at the corners, in addition, if you have some atoms at the center of the unit cell or on the surfaces of the unit cell, then you will be having then that will be called non-primitive unit cell. Alright. Now let us also have the idea of lattice points. So lattice points are what? Those are some points in crystalline structure which are similar to that the structure, the real structure of the crystal. It is just like a kind of frame of reference kind of thing. Now see, suppose I have these dots as lattice points, and we have the real atoms exactly superposing those lattice points, right? Then the unit cell will be having the atoms at the corners or in addition in other positions also, and sometimes lattice points may not superimpose on the actual atomic structure. That means it may shift somewhat, but still lattice points are kind of frame of reference, so that in most of the cases, for simplicity purpose, we always consider that the lattice points are superimposed on the real atomic structure, so that it becomes easier for us to study them. Alright, so here if you consider this unit cell, so these are our lattice points, and if I fit the real atoms at these lattice points, so it will look like this, because real atoms will be bigger inside. These are the points, lattice points only, and real atoms will be bigger inside, and they will be touching each other. And it depends on the arrangement how they are situated inside the unit cell. It will depend on what is the crystal, and depending on that we will have different kinds of unit cells. And so next let us come to the idea of Bravais lattices. What are Bravais lattices? They are the all possible kinds of lattices present in nature. And Bravais actually worked on this particular topic, and the name has been coined after him only. And in two-dimensional case, we have 5 Bravais lattices, and in three-dimensional case, we have 14 Bravais lattices. Those we will be discussing later on. And what are those different kinds? For example, let us take one simple example, this one. If the lattice is like this, so it will be simple cubic because the sides are equal. The Bravais lattice depends on the length of the sides and also the angles made by different surfaces with each other. Okay, so depending on that, we have a total of 5 lattices, Bravais lattices in 2 dimension, and 14 Bravais lattices in 3-dimensional case. Now let us move to the idea of Miller indices. So Miller indices are 3 numbers with the help of which we can denote a set of parallel planes in crystalline solids. Okay. So let us now consider one unit cell in 3-dimensional crystalline structure. So this we have drawn like this, and let us, for example, take this plane, this shaded plane, and this plane is parallel to this plane also, and another parallel plane will be somewhere here, which will be part of the next unit cell, right? So this kind of parallel planes, which we can imagine, all of them together can be represented by 3 numbers, and those 3 numbers in general are represented by HKL within small bracket. And how to find these numbers? So for that we take this plane, which is making intercept with x-axis, and it is parallel to y and z-axis. It is in the yz plane. So to find Miller indices, what we do? We take the plane in the unit cell of which we want to find out the Miller indices. For our case, now the plane is this one, A, B, C, D. Right? So what we do, we first take the intercepts. What are the intercepts? Right? So the intercepts made by this plane ABCD with x, y and z axis are A with y axis, no intercept, that means infinity. With z axis also, no intercept, that means infinity. Right? So then we find what is the coefficient. Here 1 into A, this is actually infinity and infinity. So then take the reciprocal. So the steps are like this. First find the intercepts, then find coefficients of the intercepts, which are 1, infinity, infinity. Then take the reciprocal, and it is 1, 0, 0, reciprocal of infinity, that means 1 by infinity is 0. So 1, 0, 0. So your Miller indices for the plane ABCD will be 1, 0, 0. So this way we find Miller index of any particular plane. Next, suppose we consider this kind of a plane. This one. So this particular plane, which is inclined and making intercepts with all the 3 axes. Okay. So first let us find what are the intercepts. The intercepts are with x-axis A, with y-axis B, with z-axis C. So follow the same procedure. So find the coefficients 1, 1, 1. Find the reciprocals of the coefficients, again 1, 1, 1. Therefore, your Miller indices for that plane, that inclined plane, will be 1, 1, 1. So Miller index of this plane is 1, 1, 1, and Miller index of this side plane is 1, 0, 0. So similarly, you can find Miller indices of all different planes, and just by finding out what are the intercepts made by the 3 axes. Alright. Now let us take another example of this plane. This plane is making intercept a by 2 with x-axis, b by 2 with y-axis, and c with z-axis. Okay. So first write down the intercepts a by 2, b by 2, and c. Then take the reciprocal of the coefficients. Reciprocal of the coefficients are half, half, 1. So reciprocals will be 2, 2, 1. So the Miller indices are 2 to 1. How to go in the reverse way? Suppose you are given this one. You have to draw the plane. How? You can draw it. The Miller indices are 2, 2, 1. So you take the reciprocal. It will be half, half, 1. So that means half intercept with x, half intercept with y, 1 intercept with the z-axis. Coefficients of the intercepts will be likewise. And you can then find the 3 points of intersection, half of A, half of B, and 1 into C. So mark the 3 points, join them with each other. So you will be getting this particular plane. And this particular plane will be having the Miller indices of 2, 2, and 1. Right? So now let us do the reverse thing. That means if you are given the Miller indices, how to find the location of the plane or how to draw the plane. Right? So let us again take the example of the same plane 1, 0, 0, and then how to draw the plane in one unit cell. Suppose this is one unit cell. X, Y, Z, and you see what are the Miller indices 1, 0, 0. So it is making intercept 1 because reciprocal of 1 is 1. So 1 into A means A. Next 0. So reciprocal of 0 is infinity. That means it is not making any intercept with y-axis. So the third Miller index is 0, reciprocal of which is infinity. That means it is not making any intercept with z-axis as well. So that it will be parallel to the yz plane, right? So that this is intercept with x-axis, so this will be the plane. So this is how we can find out the plane if the Miller indices are given. So Miller indices are given as 1, 0, 0. So 1 is the intercept with x-axis, infinity is the intercept with y-axis, and infinity is the intercept with z-axis, right? So this way we can draw all planes represented by some Miller indices. Okay. Now let us know the idea of directions, particular directions represented by 3 numbers again, but this time within the big brackets. Okay. If I write within big bracket 1, 0, 0, this means that this is a particular direction which represents a direction perpendicular to the plane having Miller indices 1, 0, 0, right? So first draw the plane 1, 0, 0, then drop one perpendicular. You can drop the perpendicular anywhere, but if you join that perpendicular to the origin and draw it linearly like this along the x-axis, so you can assign this name 1, 0, 0 to this particular direction. So this we call it O, this A. So OA is the direction within big bracket 1, 0, 0, right? Similarly, this direction will be what? For this plane, what is the Miller indices? It is 0, 1, 0. So this direction, this will be 0, 1, 0. So likewise, you can draw any direction denoted by any 3 numbers. So let us now look at the unit cell of a crystalline structure. So the diagram on the left hand side is a diagram for a crystal lattice, a part of a crystal lattice, and the right hand side diagram is only one small unit of the crystal lattice, which we call the unit cell. We have already discussed what is unit cell, and you know it well, that it is the smallest unit by extending which in all directions we get the actual crystalline structure. Now let us also know what are the translation vectors and interfacial angles. Now if the unit cell that we have considered here, let us consider that it is making intercepts small a, small b and small c with the three crystallographic axes x, y, z, right? And what are crystallographic axes? Crystallographic axes are the axes of the real crystalline structure, and they are not necessarily the coordinate axis x, y, z, right? So it means that x, y, z axis that we have drawn here, they are not necessarily mutually perpendicular to one another. And the angles between any two axes, crystallographic axes, that also is not necessarily 90 degree like the coordinate xyz axis. Okay, and so these angles between any two crystallographic axes denoted by alpha, beta, gamma, they are called the interfacial angles, and the vector form of the intercepts made with the three crystallographic axes by the unit cell, they are known as translation vectors. So this is the basic idea of translation vectors and interfacial angles. And if you know the values of these interfacial angles alpha, beta, gamma, and also the numerical value of the translation vectors a, b, c, then you can know what is the actual crystalline structure. And depending on the values of alpha, beta, gamma and a, b, c, so we have different Bravais lattices. In 2 dimension we have 5 Bravais lattices, and in 3 dimension we have 14 Bravais lattices in total. And all the shapes of the Bravais lattices depend on the values of a, b, c and alpha, beta, gamma. So next let us have a look at the Bravais lattices in 2 dimension. There are 5 types of Bravais lattices in 2 dimension, namely oblique lattice, rectangular primitive lattice, rectangular centered lattice, square lattice and hexagonal lattice. So for example, if you take the oblique lattice, you can see in 2 dimension we have only 2 translation vectors, a vector and b vector, and the angle between them is gamma. So in this particular case of oblique lattice, the sides of the unit cell are unequal. That means the translation vectors, numerical value of the translation vectors are unequal. A vector in magnitude is not equal to b vector in magnitude, or very simply speaking, a is not equal to b, and the angle between them is also not equal to 90 degree. If this condition is satisfied, that a is not equal to b, gamma is not equal to 90 degree, then the lattice, corresponding lattice, is called oblique lattice. Okay, so now take the case of another one, rectangular primitive lattice. So in rectangular primitive lattice, what we have, a is not equal to b, but the angle between them is 90 degree, right? And we have the lattice points only at the corners, so that will be called rectangular primitive lattice. And in rectangular centered lattice, in addition to the corner lattice points, one additional lattice point is there at the center. Okay, so that is why it is called rectangular centered lattice. In square lattice, the sides are equal, the sides of the unit cell are equal, that is A equals to B, and also the angle between them is 90 degree, gamma is 90 degree. In case of hexagonal lattice, the sides are equal, and that means A is equal to B, and the angle between them is gamma is 120 degree. Okay, so these are the 5 types of Bravais lattices in 2 dimension. So these are the Bravais lattice in 3 dimension. So already I have told you what is a primitive lattice and what is non-primitive lattice. And a simple structure, simple lattice is primitive one, where we have the lattice points or the real atoms or molecules only found at the corners, 8 corners of the unit cell. Then other non-primitive lattices are also there. Either they are face centered or body centered, or sometimes they are also called base centered. And how we can identify them? That if in addition to the 8 corner atoms we have some additional atoms, then they are non-primitive. If the additional atoms are found on the surfaces, the center of the surfaces, then it will be called face centered. If the additional atoms are found only at the top and bottom surfaces, then that will be called base centered. And if the additional atom, one additional atom is found only at the center of the unit cell, then that will be called body centered structure, right? And there are different categories like cubic, tetragonal, then hexagonal, orthorhombic, rhombohedral, monoclinic, triclinic, etc., depending on the values of the translation vectors and the interfacial angles. And in addition, if they are having different kinds of arrangement of atoms, then accordingly they will be called either simple, face centered, body centered, or base centered, etc. Okay, so in total we have 14 Bravais lattices, and namely they are simple cubic, face centered cubic, body centered cubic, simple tetragonal, body centered tetragonal, hexagonal, simple orthorhombic, body centered orthorhombic, base centered orthorhombic, face centered orthorhombic, then rhombohedral, and then after that simple monoclinic, base centered monoclinic, and triclinic. So these are the 14 Bravais lattices in 3 dimension. So these are the specifications of 3-dimensional Bravais lattices. There are 7 broad categories of 3-dimensional Bravais lattices: cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic. Cubic has got 3 subcategories: simple cubic, face centered cubic, and body centered cubic. Tetragonal has got 2 subcategories: simple tetragonal and body centered tetragonal. Hexagonal doesn't have any subcategory. Orthorhombic has got 4 subcategories: simple orthorhombic, body centered orthorhombic, base centered orthorhombic, face centered orthorhombic. Rhombohedral doesn't have any subcategory. Monoclinic has got 2 subcategories: simple monoclinic and base centered monoclinic. And triclinic doesn't have any subcategory, so that we have all together 7 broad categories, and in total 14 3-dimensional Bravais lattices. And the lattice parameters you can see from the list. Now let us have a look at the sodium chloride crystalline structure. We have marked sodium plus ions as green dots and chlorine minus ions as red dots. And let us take one sodium plus ion situated at the point 0 as our reference ion. And let the translation vector of this cubic structure is denoted by small a. Then if we notice, then we can see that at a distance of small a, the sodium plus ion is surrounded by 6 numbers of chlorine minus ions, and these chlorine minus ions have been denoted by positions 1. And then at a distance of root 2a, there are 12 sodium plus ions. These positions have been marked as 2. And at a distance of root 3a, we have again 8 chlorine minus ions, and these have been marked as points 3. And the 6 chlorine ions, which are at the distance of small a from the reference central sodium plus ion, they are the nearest neighbors of the reference ion. Okay, the nearest neighbor means that what is the total number of the atoms or ions or lattice points at the closest distance. So this is a three-dimensional view showing the number of atoms per unit cell of simple cubic, FCC and body center cubic structure. And this is the realistic diagram of the actual atoms. And here you can see clearly how the atoms will be situated inside one unit cell. So at the corners you have 1/8 part of one atom. In case of face-centered cubic, you will be having the corner atoms. Additionally, one face-centered atom on each surface, and half of that atom will be inside the unit cell. And in case of the body-centered cubic, there will be one central atom. Okay, so this diagram can give you a better visualization. You have already seen that the FCC and BCC structures, they are not primitive, right? So if you look at the diagrams of unit cells of FCC and BCC structure, then you can see that either one additional atom is at the center, or sometimes there are atoms on the surfaces. So these unit cells are not primitive. But suppose you want to draw the primitive unit cell for FCC and BCC, then how you can draw the primitive cell? In case of FCC, you take the surface atoms, and they have been marked as 1, 1, 2, 2 and 3, 3, right? They are the surface atoms. And then also you take the atom at two extreme corners, O and A, and then you connect these points as shown in the diagram. And then after completing the diagram, you will be getting one unit cell. And if you observe that, you will see that there is no atoms on the surfaces, nor there are atoms at the center. Okay, so that means this is one primitive cell. The unit cell that now we have got drawn by red lines is primitive, right? So this is primitive unit cell of FCC. This is for the left hand side diagram. Then come to the BCC structure, and which is denoted by the right hand side diagram. In this case also you can draw the primitive unit cell. How? The corner atoms are there, and the body centered atom is there at the point O. Then if you consider the body centered atoms of adjacent unit cells, if you observe the position 1, that corresponds to the body centered atom of one unit cell, which is just above the surface ECBF. Then the position 2 denotes the body-centered atom of the unit cell, which is on the right hand side of the surface FBHD. If you observe the position 3, that corresponds to the body-centered atom of the surface, which is on the front side of the surface EFDA. Okay, so if you take these 3 positions and also you take the central body-centered atom O, then take other corner atoms of the BCC structure E, then B, F, D, then join them as shown in the diagram. Then the unit cell that has been drawn here in red boundaries, that you can see there is no more atoms at the inside the unit cell, nor there are atoms on the surfaces of this new unit cell. Okay, so that means it is primitive. Okay, so that new unit cell is the primitive unit cell of the BCC structure. Okay, now let us know what is packing fraction. It is sometimes also called packing factor. Now take the example of simple cubic, FCC and BCC. And packing factor, it is defined as the ratio between volume occupied by atoms inside the unit cell and the total volume of the unit cell. That means total volume occupied by atoms inside one unit cell divided by total volume of the unit cell is called packing fraction. Now, for example, let us take first the case of FCC and BCC structure. In case of FCC, if you look at the arrangement of the atoms, then we will be seeing that here the atoms on the front surface will be arranged as shown in the upper diagram. At the 4 corners there will be 4 atoms, and at the center of the front surface there will be 1 atom. Half part of the central atom will be inside the unit cell, and at the 4 corners there will be the 1/8 part of the atoms inside the unit cell. Now, to find the packing factor, we have to know the volume occupied by the atoms and total volume of unit cell. Total volume of the unit cell for cubic structure is always AQ, where A is the translation vector. That means A is the sides of the unit cell, right? So that is constant. And what about the volume occupied by the atoms? It will vary depending upon whether it is simple cubic or FCC or BCC, right? In case of FCC structure, look at the arrangement of the atoms. Then if you look at the diagonal of the front surface, that means the line joining the 2 extreme corners A and B, then AB is the total length between these 2 extreme points A and B, and that is numerically equal to 4R. If you look at the diagram, you will see that at the corners there will be 2 atoms, and at the middle there will be 1 atom, right? So the diameter, if the diameter of one atom we call it small r, then the full length AB will be small r plus twice r plus r equals to 4r. That means AB will be under square root 2 into A, or AB square is twice A square, right? So that is why we can write that 4r square is equals to twice A square, because AB is 4r on one hand and is also equals to twice a square on the other hand. If you look at the triangle ABD, then AB square equals to a square plus a square equals to twice a square, right? So from that we can find out the relationship between R and A. Okay, so similarly we can find a relationship for between R and A in case of BCC also. In case of BCC, the length AD is equal to 4R, and from geometry AD is also equal to 3 under square root 3 into A, that is AD square equals to 3A square. So that we have 4R whole square equals to 3A square. So in case of BCC also we have got the relationship between R, the radius of one atom, and translation vector A. So now we can easily determine the packing factors of simple cubic, BCC and FCC after knowing the relationship between the values of small r and small a. R is the radius of one atom and small a is the translation vector of the cubic structure. Now in case of simple cubic, the volume occupied by the atoms inside the unit cell will be equal to 4 by 3 pi r cube into 1, because there will be effective number of atoms inside the unit cell is 1 only, right? So that value small v in case of BCC will be 4 by 3 pi r cube into 2, because there are 2 effective atoms for BCC, and for FCC there are 4 effective atoms. Therefore, the small small v value will be equal to 4 by 3 pi r cube into 4. Alright. And the capital V volume, that means the total volume of the unit cell, is a cube in all the 3 cases. So that we can easily find out the value of the packing fraction. And as we know the relationship between R and A, just we have discussed already. Then we can put that value of R in the expression for packing factor, and then correspondingly we will be getting the packing factors for simple cubic structure as 0.52, for BCC it will be 0.68, and for FCC it will be 0.74, right? So this is how we find out packing fraction. Then there are few more terms which you should be knowing are planar density, linear density. Planar density is the ratio of number of atoms in a plane to the area of the plane. Linear density is the ratio of number of atoms along the direction vector to the length of the direction vector. And there is another term, coordination number, that we have already discussed. It is the number of nearest neighbors, and coordination number for as simple cubic is 6, for FCC 12, for BCC 8. You can take any lattice diagram for cubic structure and you can easily identify them. Now let us come to the idea of interplanar spacing. So we have already discussed what are Miller indices, and let us consider a set of parallel planes denoted by the Miller indices HKL. Then the distance between any two corresponding planes of this set of planes will be called interplanar spacing. That means you take any two planes of this set of parallel planes, that distance between them as shown in the diagram DHKL is called interplanar spacing. So interplanar spacing can be derived, the expression for interplanar spacing can be derived using the law of direction cosines, and it is given as DHKL is equal to 1 by under square root h by a whole square plus k by b whole square plus l by c whole square. This is the general formula for interplanar spacing. Now let us come to the concept of reciprocal lattice. So you already know what is lattice structure in crystalline solid. So let us call that unit cell as the direct unit cell, or the lattice as the direct lattice. Okay, so let us take one unit cell of the direct lattice as shown in the upper diagram, and here we have A vector, B vector, C vector as the translation vectors. Okay, then we take the reciprocals of the magnitudes of the three translation vectors, and the reciprocal translation vectors will be drawn in that order only. That means if we have A, small a less than B less than C, that means out of these three translation vectors, A was the smallest, C was the largest. Okay, then the reciprocal translation vectors will have magnitude in such a way that A star will have the largest value and C star will have the smallest value. And what about their direction? Their direction will be in such a way that A star will be perpendicular to YZ plane, B star will be perpendicular to XZ plane, C star will be perpendicular to XY plane. Okay, so in this diagram, the lower diagram for the reciprocal lattice, we have the directions of A star same as A, B star same as B, C star same as C, because originally A vector, B vector, C vector, they were making 90 degree to one another. Okay, but if they are not making 90 degree to one another, then the reciprocal lattice vector will be little bit tilted. Okay, so that we can see in our next diagram. So this diagram shows two different examples, monoclinic and orthorhombic case for direct and reciprocal unit cells. And here we can clearly see that if originally A vector, B vector, C vector, they were making 90 degrees, then the reciprocal lattice will not be tilted, but the lengths of the sides will be different, will be in the reverse order. If A was the highest, then in the reciprocal lattice, A star will be the lowest. Then if the A, B, C, they were not making 90 degree in the direct lattice, then of course it will be tilted, because the direction of A star vector is perpendicular to the original plane containing the vectors B vector and C vector, right? So it will be a little bit tilted, as shown in the case of monoclinic reciprocal lattice. Okay, so this I'm not going into details, and maybe in some other class we'll be discussing it a little more. So I hope that you have by now got some idea of crystalline solids and its properties, and some very basic idea on reciprocal lattice. And reciprocal lattice is also another important idea with the help of which we can draw the Brillouin zones, which are helpful in understanding band theory. So that we will be discussing in some different class. Okay, so that's all for today. Thank you.